Good evening, everyone. I'm Mark Miller. I am the current director for the Institute for Earth, Ocean, and Atmospheric Science here at Rutgers. And this lecture, this distinguished lecture, is co-sponsored by the Rutgers Climate Institute and America Converges Here, which is a program which celebrates Rutgers history and diversity. So our speaker this evening is Dr. Lonnie Thompson. He's a distinguished university professor at the Byrd Polar Climate Research Center at The Ohio State University. Lonnie is among the nation's most elite scientists. He's produced over 220 scholarly publications, and he's become an international symbol for changes in glaciers and the message that can be conveyed about the history and future of Earth's climate system. Among his very large and long list of awards are some of the most prestigious in science. He was elected a member of the National Academy of Sciences in 2005. He was awarded the United States Medal of Science in 2007 by the President of the United States at the White House. He was elected as a foreign member of the Chinese Academy of Sciences in 2009, awarded the Benjamin Franklin Medal by the Franklin Institute in 2012, elected as a member of the American Philosophical Society in 2006, a fellow of the American Geophysical Union in 2001, and he has received numerous honorary degrees, including recently an honorary doctoral degree in 2013 at the 257th commencement for the University of Pennsylvania. What is truly remarkable when you read this legacy of work is the 61 expeditions that Lonnie has either participated in or led in his 40-year career. It's an amazing list. In fact, as recently as 2016, he was a field team leader of a 60-member expedition to the Goya ice cap in the western Kunlun Mountains of China. And what is really amazing is if you look further in his record, you realize that his first trip to that area was in 1990, 26 years. The media has not lost at all any interest in what Lonnie does. In fact, he has been documented in many ways, including a PBS special called Against All Odds that really documented his contributions to science. There was a 2000 Nova special about Lonnie. And in 2006, he provided the American Association for the Advancement of Science's briefing to the Congress on the present impacts of climate change. So I hope you'll all join me in offering a very warm Rutgers welcome to Dr. Lonnie Thompson.
Thank you, Mark. It's my pleasure to have an opportunity to speak this afternoon. And I've been very fortunate to actually really enjoy what I do. And I think for the younger people, this is key. And if someone had told me when I was in graduate school that you could ever win the National Medal of Science looking at ice, I would have said that's not very likely. But I've been very fortunate over the years to have a good team of people, and it can't be done without a team, both at the university at Ohio State, but in 16 countries in which we've drilled and recovered records. I mean, it's really a global effort. So this is the current members of our team. And I want to point out Ellen Mosley Thompson. She has done a lot of work in Antarctica and Greenland. And when we were raising our daughter, the field work in the mountain regions are out of phase with Antarctica, so there was always a parent at home while she was growing up. So, major contributions over many years. So today I want to talk about the Earth's climate system, the fact that the Earth is warming, and that debate is actually over. The global climate change involves many changes, and it's not just temperature, and I'm sure you've heard about many of these: precipitation, sea level changes, ocean acidification, ecosystem changes, and melting glaciers. Weather and climate are very different, and then changes in the climate system are driven by both the natural and anthropogenic. We look at glaciers, and glaciers serve as recorders of climate change. If you go high enough or in a cold enough environment, every year the snowfall is preserved. and it can be recovered and give you a lot of different details of climate and also the forcing of climate through change. But glaciers are also an indicator of climate change because they respond to what's going on in their environment. I'll give some evidence for recent acceleration in the rate at which we're losing glaciers around the world. And finally, I want to turn to people. In the last few years, I've had fortunate to give a lecture to behavior analysts, 5,000 international behavior analysts who study us and why we do what we do. And to me, this is a much more complex question than climate change. But there were, in preparing for that, I looked at some of the earlier work that B.F. Skinner did, and he was very optimistic when he was young and middle age, but by the time he had reached 80, he had become pessimistic about human beings acting in their own best interest. And there were a couple things that relate to climate change issues. And one is, one of the characteristics that we have is that immediate consequences outweigh delayed consequences. We're kind of here and now people. And secondly, consequences for the individual outweigh consequences to others. You might be concerned about sea level displacing people in Bangladesh, but you're more concerned when it's your house that gets displaced. And then finally, I want to talk a little bit about our options and our greatest challenges in the 21st century. So if we look at Earth's climate record, the temperature record, certainly the temperatures have been warming dramatically since we've been keeping records, going back to 1880, coming forward in time. And 2016 was the warmest year on record, followed by 2015, 2014, 2010, 2005. And every year we seem to be breaking new records. The climate of the last 40 years has been very unusual, in part because of the increase in frequency and intensity of extreme weather events. Everything from heat waves to prolonged droughts and fires and floods. And these are what the Intergovernmental Panel on Climate Change models predict, that these type of system responses to global climate change will become more frequent as we go forward in time. If you look at each successive decade, 10-year intervals has been warmer than the last, and you can really see the application of these temperature changes in the Arctic. And this is one of the characteristics of the ongoing changes. I like this diagram for showing the difference between climate and weather. I have a couple dogs, and if you ever take them out walking, they go from fire hydrant to candy wrapper, and while you're going down the street. And so in this cartoon, the walker is the climate. It's the long-term trends, and we generally look at the 30-year averages of the weather, and the dog is the weather. And probably Mark Twain said this best when he said that climate is what you expect, and weather is what you get. And so I was looking at temperature records in this part of the world, in Newark, and the 30-year average temperature should be about 1.5 degrees C. This February, this is for the month of February, and this February it's been 4.6 degrees C in this region. But this, if you go back 2 years to February of 2015, the temperature for February was minus 5.2 degrees C. And this is the variability that exists in weather. And if you look at 2015 globally, you can see that over eastern part of the US and eastern Canada, it was extremely cold, but February for 2015 was the second warmest February ever recorded for the planet. So there's a lot of spatial variability that takes place. So where is the heat going? Most of it is going into the oceans, 93.4%, and a very small amount is actually going to heating the atmosphere and the land surfaces and melting glaciers. In the past, when we've had these El Nino events, the periodic heating of the equatorial Pacific has been very effective in transferring heat from the oceans to the atmosphere, and you can see that in the long-term temperature records. The Decadal trends, strong ocean warmings, these go back to 1955. They come forward in time and they show the depth at which the heat is being transferred into the oceans as you come to this period from 2005 to 2011. So a lot of heat is being stored into archives on the planet. And of course, if you look at what's happened to sea ice since we've had satellite observations, this is for the end of September each year, and 2012 was the lowest sea ice recorded. But it's kind of interesting when you look at the details from month to month. This is only September. And if you look at 2012, which is the green line in this diagram, and you can see how low it was in September relative to 2016. But if you look at the months of October, November, and December, we have the lowest levels of sea ice in the Arctic that have been measured since we've been keeping records of that. But probably one of the things that's most concerning is if you go back to 1984 and you look at September, and you look at sea ice that's 4 years or older, you can see it here in white. This is a white area. And there's very little a small amount of 0 to 1 year old sea ice. But if you come forward to 2016, you can see this totally reverses. There's very little of the old 4 years or older sea ice, and most of it is seasonal sea ice. So it gives you a picture of what's going on there. Then there are hidden impacts of, I talked to a number of graduate students today and who are looking at the water that's stored on the surface and going into the glaciers in Greenland. And of course, the water goes down through these moulins, lubricates the bottom of the ice, and the ice moves faster into the ocean, and you get faster responses of sea level rise. But if you look in the longer term, we've had many natural mechanisms that are working right now, impacting the climate system. Changes in solar activity, 11-year cycles, 90-year Glacier cycles. Energy coming from the sun is extremely important. There are changes in the amount of aerosols in the atmosphere from major volcanic eruptions, and this has a climate impact. And then there's the internal variability in the climate system, ENSOs, monsoons, and the like. And then on top of that, we have the human factors, the non-natural, the changes in the composition of the atmosphere, changes in aerosol particles, and some of these lead to warming and some to cooling, changes in reflectivity and the albedo of the Earth's surface and hydrological cycle as we clear forests for more crops. So there are a lot of ways that we are impacting the climate system. Charles Keeling started measuring CO2 in the atmosphere in Mauna Loa back in 1958 when it was about 315 parts per million by volume, and we're now above 400 parts per million by volume. And it's increasing very rapidly, and you can see this, you can log on and see these numbers at any time. So here, if you look at January 2nd, 2016, and then you look at January 2nd, 2017, and the thing that even though we've had many international meetings on this issue, CO2 continues to rise and accelerate in the atmosphere. And we have in the ice cores, a long-term history of how CO2 has varied, along with many other greenhouse gases, going back over 800,000 years. And if you look at this figure, you can see that during the cold periods that we can see in the Antarctic temperatures, CO2 is very low, 180, 200 parts per million by volume, and during the warm periods it reaches 280 to 300. If you look at where we are today, you can see that in that 800,000 year history there's no analog to those values. And this is what is of concern, but perhaps of more concern is where we're projected to be at the current rates of CO2 increasing. And we talk more about CO2 than other greenhouse gases because of the long residence time this gas has in our atmosphere. It remains for decades to millennia, and there's been a lot of experiments looking at, okay, what if we found an alternative energy source today? How long would it take to pull down the CO2 that's in the atmosphere? And if you look at these, you can see that if you look out 100 years from now, we'd still have 33% of what we've released impacting the climate on the planet. If you look out 1,000 years, you still have about 20% impacting the climate. So it takes a long time to remove this through natural systems to get it out of the atmosphere. So these are the concerns, and it's interesting to look at the geologic record and see how far back do you have to go to find 400 parts per million by volume of CO2 in the atmosphere. And you have to go back to the Pliocene, that's about 3 million years ago. And during that period of time, the Earth's temperature was 2 to 2.5 degrees C warmer, and sea level was about 22 meters higher. And so if you look at the east coast of the US here, you can see where sea level was at that time. And if you look at the polar regions, you can see today the amount of ice in Greenland and what it's projected to have looked like 3 million years ago. And similarly for Antarctica and 3 million years ago. So I think this is probably a lesson when we look forward in time to what's possible. Another, I think, concerning diagram is this, where you look at the cities of the Earth, as you can see from the International Space Station, and where that electricity is coming from, 65% from fossil fuels. And companies like General Electric have done projections of what will the Earth look like 13 years from now, by 2030. And when you look at that, you say, you know, where's that energy going to come from? And if it's coming from fossil fuels, then the climate of this planet will be much, much different than it is today. So these are the concerns. So we've spent a lifetime looking at ice, recovering records, looking at the history recorded at different latitudes and different continents. And as I said earlier, we've drilled in 16 countries in addition to Antarctica and Greenland to look at that history. But it didn't start that way, and I think it's important if you're just starting out in your science career to look at how things have changed. So I'm going to use this as an example. This is the margin of a tropical ice cap, the Quelccaya ice cap. Those are annual layers. It's a very distinct wet and dry season in the tropics. And if you go high enough, that is recorded in the ice, and it's easy to see how you could take a drill and recover that history. This is an ice core, and normally, when I was a graduate student, your timeline would start the year that you went to drill. And I'm going to show you that that's no longer the case for many glaciers on the Earth. But I want to take you back to the beginning, and I think this is an important lesson for young people. It's important to experience failure because we learn more about failure than we do from success. And it's good to do it when you're young because no one will remember. And so it's a good time to take a chance. And if you go back to 1974, when I was a graduate student, and there's a lot of serendipity in life. There happened to be a fellow in our Institute of Polar Studies at that time, John Mercer, who had made atlases of the glaciers of the world, South America, North America, and he had boxes of aerial photos. And it was in this time we got this idea, wouldn't it be great if we could connect ice core records from Antarctica with Greenland with something in between? And so we found this Quelccaya ice cap, and we took the photos to Washington, to polar programs that funded ice core research, talked to Jay Zawali, and made the presentation and said, wouldn't this be great if we could do that? And he listened, and then when he was finished, he said, you know, Lonnie, that sounds very interesting, but you know I can't fund it because it's not north of the Arctic Circle, it's not south of the Antarctic Circle, and that's all they funded. So I actually went to Antarctica in 1974, in West Antarctica, down there 2 months. And in February, I got a telex, that's what they used back then, from the program manager saying that I have funded all of my real science projects and I have $7,000 left. What could you do on that tropical glacier for $7,000? And I telex back and I said, I think we could get there. And that's what we did in the summer of '74. And this led to our first attempt to drill a tropical glacier, and they're a lot different than what you find in the polar regions, but being young and naive, I thought, we bring a drill from Antarctica, we bring a generator from Antarctica, we make a contract with the Peruvian Air Force for this Bell 212 twin-engine helicopter. No airports up there, but we can bring the fuel in by train, and so these drums are the fuel. And then we tried to get up there early in the morning and late in the evening, but at 19,000 feet, this helicopter would just fall, and there was no way they were going to get near it. And it was a 2-day journey by horse from the end of the nearest road, and there's no way you could get that drill up there. And all my colleagues were telling me I needed to get back in the polar regions. That's where the real science was. And this is when you make critical choices. And this is the first time we thought about using photovoltaic cells to power a drill. This is 1983. And not even the National Science Foundation thought this was a good idea. And more importantly, we had to write a proposal, and it had to be reviewed. And we'd already failed once. And so we wrote a proposal, and Willie Dansgaard, one of the pioneers in our area, and a person I respect very much, he was a reviewer, and he sent me a copy of the review, and it said, the Quelccaya ice cap is too high for human beings, and the technology does not exist to drill it. And fortunately, there was a program manager, Hassan Verji, who looked at that, and he said, Willie might be right, but we won't know unless we try. And so we built this drill. We tested it on the parking garages at Ohio State University. We brought in blocks of ice, drilled through it, seemed to work. But 2 weeks before leaving on that expedition, I passed the MBA exam in the Fisher School of Business, because I figured if I failed the second time, I'd have to have another option for the future. So it's good to have options. So one of the things I learned was that those who question your ability may actually do you much greater service than those who give you fake praise. And by meeting those challenges head on, you'll become more sharper and more competitive in what you're doing. So this was a crew, and I had a lot more hair back then, but we didn't have porters. We had to carry everything up, assemble the drill, and this is what this first solar-powered ice core drill looked like. And it worked beautifully, and we drilled not 1, but 2 cores to bedrock. We didn't have technology to keep the ice frozen, so they were cut into 6,000 samples. And one set of samples we sent to Denmark, to Willie Dansgaard's lab, and he did the isotopes, and he was so excited. And he became our greatest supporter of why we should get ice from these high mountain regions. So I think you need to believe in yourself, but be flexible and seize any opportunity that will create other options for you. So from that, we've gone on to build clean rooms, where we measure dust particles and chemistry and black carbon. We have mass spectrometers to measure isotopes in the cores. We have over 7,000 meters of core stored at minus 30 degrees C. It's the only tropical collection on Earth. And we design and build the drills that we use to recover these ice cores. They have to be lightweight and portable. So this is what a typical drilling system, this is on some of the Quelccaya ice cap, looks like. And all that stuff has to be small enough so one person can carry it to assemble the drill. We continue to work with the technology where our solar panels now just roll out on the surface. But we designed generators, diesel generators that will run at 20,000 feet in a very cold environment for providing power on some sites where we drill. Logistics, always difficult if you're in Tibet. There are usually no roads going out to the mountain ranges where the ice fields are located. And once you drill the cores, then you've got to get them out of there, and you've got to keep them frozen until you get them back to Columbus, Ohio. And that's a challenge. And if you're in the Himalayas, you use Sherpas and porters. So these are frozen ice cores going down. But when you get down to the margin, you're still 4,000 feet from where trucks can come out on the plateau. And so you have to use local transportation. So if you're in the Himalayas, this is the local transportation. These are yaks, and they are adapted for high elevation. There are 6 meters of frozen core in each of those insulated boxes, so 12 meters per yak. And we drill 500 to 600 meters, so you have to have a whole team of yaks to get the cores down to the trucks. Then there's a dash day and night across the plateau to Lhasa, where there's a freezer. Then they're air cargoed to Beijing, go through Chinese customs, air cargoed to Chicago, go through US customs, go on a freezer truck, and they come down to Columbus, Ohio. So they're usually in transit for a month from the time you actually recover them. So the logistics, and you need a lot of people to work to make those things happen. We didn't know it at the time, but it turns out that Quilcaya ice cap in the Andes of Peru is the largest tropical ice cap on Earth. We went back to this site in 2003 when we had the technology to keep the ice frozen, so we could bring back frozen core and preserve that for the future. Now, these cores have a wonderful annual history in them. And so here you can see 2 of the parameters, and we measure probably 15 different, but I'm not going to bore you with them. This is from about 1830 back to 1800, and you see the annual variations in isotopes, which is a temperature proxy that we use at these high elevation sites. In every dry season, there's a dust layer. You measure the thickness of those dust layers, and you have the net balance, how precipitation has changed through time. And there are very few archives that allow you to actually reconstruct that. What we're always impressed in is the reproducibility of these records. This is the very first core that Willie Dansgaard analyzed. These are decadal averages for the last 1,000 years from Quilcaya. The reds are warmer periods. You can see the little ice age here. Then coming into the 20th century, back in 1983. 20 years later, going back, drilling at the summit, here's the record in the isotopes measured in our lab, and you can see the same features. And we had the technology to also drill the North Dome, so we got multiple cores to bring back and store for the future. And because you have those annual dust layers, you can reconstruct the history of precipitation over this period of time. The brown areas are periods where precipitation was below normal. And you see the onset of the Little Ice Age, it was wetter. As you get into the middle of the Little Ice Age, it becomes dry. And then the 20th century has been wetter than average. So you can put what's going on in that part of the world into a time perspective. Back then, we thought that you might get a 4,000-year history out of a tropical glacier, but probably nothing more, until we went to Huascaran, which is north of here. It's a higher mountain. It's at the drill site here is about 6,050 meters, and this mountain is the highest tropical mountain on Earth. And we drilled in the col here, and that record actually spanned 19,000 years, and it was the first recovery of ice that actually recorded conditions above the Amazon basin at 9 degrees south of the equator. And the isotopic shift here was about 8 parts per mil, very similar to what we find in the polar cores. And if you look at nitrate, it's a reflection of NOx emissions in the Amazon basin, because the precipitation comes from the easterlies. And you can see that it's very low during the colder late glacial stage and much higher in the warmer Holocene. We think this reflects vegetation changes out in the Amazon basin. And then the dust record, you can see that dust was 100 times higher during the late glacial stage, indicating dry conditions in that part of the world. So there's a tremendous history and a very long history. And we've drilled around the world, and we've been able to duplicate this isotopic shift in many sites. And you can see from the polar regions of Greenland to Antarctica, and this is the glacial, interglacial isotopic shifts that have been measured. So they're very, very large globally. So in the 1980s, the advent of this tropical ice core recovery led to the first evidence of the Little Ice Age in the tropics, the first ice core evidence of significant late glacial stage cooling in the tropics. and the first ice core evidence of major failures of the Asian monsoons. And this resulted in a number of papers in Science, and we found out that if you can get the cover of Science, your readership will go up 50%. So scientists are also impacted by what they see. And so it was an exciting time to be doing that type of work. So if you come into the present time, all the red areas you see here are places where there's documented ice loss taking place in the Arctic, the Antarctic, and over here in the third pole region of the world. And this is a place that we have been putting a lot of effort in recent years. And in 2015, we conducted the largest expedition we have ever conducted. We had 60 people from 5 countries crossing the Tibetan Plateau. Here's Lhasa, all the way out to this Glacier ice cap in the western Kunluns of northwestern China. And here we drilled on the summit of this ice cap at 22,000 feet, 3 cores to bedrock. And what makes this glacier unusual is its latitude. It's 35 degrees north of the equator, so it's the same latitude as Durham, North Carolina, and Memphis, Tennessee, so south of here. And yet it's actually a massive ice body this is the actual ice cap, covers about 200 square kilometers, but it's embedded in this mass that covers over 8,000 square kilometers. And we were able to drill the 3 cores at the summit, deep cores, and down on the plateau where the ice is deeper. And we had first gone to this site back in 1992, and we were trying to determine whether you could take an ice core and get it across the Gobi Desert without it melting. And we were able to do that. And we were able to measure the temperature in 1992 in the deep core you can see here. And then 24 years later, we were in the 2015 core. You can see how much warming has taken place in the upper part of the ice field. And then up on the summit, you can see how cold the ice is. These glaciers are frozen to the bed, so they potentially have a tremendously long record. And what we couldn't do back in 1992 was to profile the glacier, to map the bottom topography, which is extremely important for choosing drill sites. And this is what the bottom topography looks like on the plateau. So here's the drill site, and you can see where the cores were drilled relative to the surface and the bottom. So they're very deep cores for a mountain glacier. And one of the things we're looking at here is that the fact that when you talk about how old ice is, there are really 3 big drivers. One is how thick the ice is. That's very important for the time resolution in the cores. What's the annual net balance? And this is a very important amount of years you can get in a meter of ice. And it's very dry in this part of Tibet. There's deserts out, so the accumulation is very low. But most importantly is this temperature at the ice bedrock contact. The physics of ice would argue that if it's frozen to the bed, time cannot be removed. The only way you remove time is to melt it. And so the question is, how old is the ice? And right now there's a big effort to find out, to recover the oldest ice on Earth. Most people feel that it will come from Antarctica, but that may not be the case, because if you look at the profile of the bottom of East Antarctica, where the ice is over 200 meters thick, these are lakes. There are over 435 lakes. There's a river system under there, which means it's so thick, and the geothermal heat coming up, you're at the pressure melting point, and time is being removed. So it remains to be seen where that ice will actually be preserved. But in the Tibetan region, these are places that, with our Chinese colleagues, that we now have cores. And if you look at these cores, from all sites except Glacier, the records are mainly Holocene records. You can see the enrichment taking place in all across the plateau. But the Glacier record has the whole last glacial cycle preserved in ice at 35 degrees north of the equator. And we published this record and compared it with the polar regions. And so this is the Glacier record here, the last glacial cycle, 130,000 years. But we didn't publish the lower 45 meters of the core because of the concerns about the dating. And back in 1992, there was only one method for dating the core, and that was to measure chlorine-36, which was done at the ETH facility in Switzerland. And these are the chlorine-36 measurements here. And at the bottom of this core, it was chlorine-36 dead. Chlorine-36 has a half-life of 300,000 years, which would argue that the ice has to be over 750,000 years in age. So the potential here is for very, very old ice. And the first thing we do, these cores are being analyzed in the lab as we speak. The blue are the isotopes from the 2015 core, and the red is the isotopes from the 1992 core. So 24 years later, you can see the reproducibility in the very old part of the core. And this is chloride, and again, you can see the reproducibility in the record. So currently we have 3 labs that are measuring various parameters. ETH is now doing chlorine and beryllium-10. Beryllium-10 has a half-life of 1.4 million years. And we're sampling next week the O2 measurements to look at the atmosphere variations back through time, which can be compared to the Vostok core, the Epica core. And then Michael Bender is working on doing argon-40, argon-38 measurements. So using different techniques, and we're hoping that we get a convergence on the age at the bottom of this core. But the ice records many things, and one of the reasons why we look in the tropics is that if you want a history of things like monsoons or El Nino variations, these are the ideal cores to investigate. And so I'm going to give you a kind of a quick overview of what can be done here. Here we compare the composite isotopes of the cores from the Andes with the highest core from the Himalayas from 1854 to 1993 of sea surface temperatures compared to the isotope records. And you can see that they're very highly correlated to Eastern Pacific temperatures. And this is where we see the signals coming from El Ninos. And in fact, if you look at that record back through time, the red is the temperature and the blue are the isotopic values. And so you can see how you're capturing that decadal variability. In 2016, we went back to the Andes to look at what was the impact of the 2015-2016 El Nino on these records. And we have a whole series of cores from Calcaya, the first one drilled in 1976. You see the annual cycle that was preserved then. By 1991, melting was taking place at the summit, at the highest place on this ice core, and water is moving through the porous fern layer and smoothing the isotopic history. And this by 2016, you can see what it looks like here. And what we found is that during El Nino years, in 2016, you see how low the accumulation rate was. Isotopes are enriched and accumulation is very, very low. And if you go north to Huascarán, and we hadn't been there since 1993, you can see it was also a low accumulation, enriched isotopes, but you can see the annual signal is still being preserved there, which would suggest that a history is still preserved at that site. If you look at the precipitation histories, these are gauge measurements, and look at what happens in Peru during El Ninos, you can see where Calcaya is located in the south, it's always in a drought during these events. And Huascarán to the north is right on the margin of where we have wetter conditions, so it's variable. But the 2015-2016 El Nino was very unusual in that there was drought throughout the Andes, and so there was a mass loss of all the glaciers through that region. So one of the things we're looking at right now are something we call black swans. These are rare and unpredictable events that have major impacts in the world. And rapid changes in precipitation patterns, such as monsoons in India, the rest of Asia, could sharply disrupt that region's ability to feed its population. I mean, India has 1.4 billion people. China has 1.3 billion people. And so we're looking at the history in these glaciers where we have annual records. And so if you look at the records from the Andes of Peru, these cores, this Calcaya has the longest annual record in the tropics, going back 1,800 years. But each of these sites, Corapuna goes back 250 years, and Dasupu goes back about 560 years with annual resolution. And you can compare these cores on the opposite sides of the Pacific Basin. And so they're separated by 22,000 kilometers. One's in the northern hemisphere, and one's in the southern hemisphere. And if you look at the wind patterns in these areas, this is the monsoon system. This is where Dasupu is located. These are areas where there's very high fluoride concentrations in surface soil. And if you're in South America, this Bolivian high circulates the air through here and then back across where the drill sites are located. And you can look at satellite images of aerosols in the atmosphere. This is on October 28th of 2013 over in India. You can see all of the dust coming up here. This is where Dasupu is located. And if you're in South America, there's the Salar de Uyuni, which is the largest salt flat on Earth down in Bolivia. During La Nina years, it's wet, and there's often about 10 centimeters of water sitting on top of this salt flat. During El Nino years, when it's a drought, it looks like this. And when the wind blows, it looks like this. And so a lot of stuff gets picked up and circulated. And when we look at the ice core records from here and here, and we look at the last 250 years, there's a massive drought that occurred in the 1790s. And you can see it here in the chloride records from Calcaya, from Corapuna, and from Dasupu. And this suggests something very different than what we've seen in the last 100 years. And it's interesting to look at human history at that time, because by this time we had occupied much of the world. And so if you look at 18th century history, in East India, there was this East India drought with 1791 El Nino being the core of that. There were 11 million deaths that occurred in India and 600,000 in north central India in 1792. And this is before the population was what it is today. In other parts of the world, there were severe droughts in Java, Australia, Mexico, the Caribbean, and in Egypt. It's measured by Nile River discharge. And there were great social upheavals. There were, I think, 4 revolutions that took place in this period of time. So the question is whether climate played a role in this. Now, you can take these records back further, and this is decadal averages from the Himalayas and the Calcaya. And you can see these two events. They're very well dated in Calcaya, lesser so for this earlier event. So if you look at the history here, this is a map from 1795 in India. This is where in 1792 those 600,000 deaths were recorded. If you go to this earlier period in China, this was the time of the collapse of the Mongol dynasty in 1368 AD during extreme mid-14th century drought that gave rise to the Chinese Ming dynasty. And it was also a time of the plague that killed probably 30 to 60% of the population in the known world at that time. And again, the question is whether these climate events played a role. So in the 14th century, this pandemic, known as the Black Death, swept through the known world. There were European and social political structures underwent massive reorganization because they lost all their cheap labor. So the feudal system kind of collapsed. Then the Mongol Yang dynasty, founded by Genghis Khan, was overthrown in 1368 AD in the middle of an extreme drought that lasted from 1353 to 1395. So you can get a historical record in these places where people were living to compare with what you see in the ice. You can also look at the longer-term trends, the changes in temperatures, and this is a composite of the last 2,000 years, decadal averages from the glaciers in the Andes and the glaciers in Tibet. And you can look at that record. You can see the medieval climate anomaly, little ice age, and enrichment in the 20th century. You compare that to northern hemisphere temperature reconstructions that come from tree rings and historical observations. And then the actual instrumental records are on top here. And when you look at this, you can see the last 50 years are very unusual in these records. But I can tell you, if you present this at the US Senate, they look at this, they say isotopes, but the glaciers are a very good recorder of change, and this actually makes a much bigger difference. This is one of my favorite quotes. It comes from A World Without Ice by Henry Pollack. And it says, ice asks no questions, presents no arguments, reads no newspapers, listens to no debates. It is not burdened by ideology, and it carries no political baggage. As it changes from a solid to a liquid, it just melts. And so this is much harder evidence to argue with. It's hard to find old photos in the mountain regions in the tropics. We found this photo taken, it was on a glass plate, taken by Chambi back in 1935. And then we went to the same place in 2006 to find this rock. And this is what the glaciers looked like in 2006. And you can overlap these, and you can see where the ice was in 1935, the gray areas that you see here. And you can see where the ice is today, the brighter areas. And you can actually see that not only is the area changing, but they're thinning from the top down. And so you can actually document those changes. This photo I took when I was a graduate student, 1977. And this is what the place looked like by 2002. And so you get the take-home message that you're losing the history that's in the ice, but you're also losing a very valuable water resource for the people who live here. This is the largest outlet glacier coming off of Quelccaya. We started monitoring this, mapping it in 1978. And this is going to morph into 2011 so that you can see how this has changed over that period of time. So here we are by 2011. The lake here started forming in 1991. It now covers 84 acres. It's over 60 meters deep. It did not exist until 1991. But all around the margins of the ice cap is retreating. This boulder was being pushed by the glacier in 1977. In the next photo, you're going to see the end of this boulder looking out to where the ice is today. And so here's the boulder now. You see this lake is formed. This is where the ice was in 2000, 2005, 2015, and 2016. So the ice continues to retreat to higher elevations. But this ice cap is very unusual, and it keeps things presenting new information. In 2002, while we were waiting for the horses to show up, we were on the backside of one of these lakes, and we found this plant deposit. It's a wetland plant, no woody tissue, perfectly preserved, and we were able to collect that and then carbon-14 date it. And these plants were about 5,200 years in age, and they tell us that the glacier hadn't been smaller for over 5,200 years. Otherwise, these plants would have decayed because they have no woody tissue. And the rate of change is so dramatic. This is in 2002. Here's the plant. 3 years later, you see where the wall is. Here's the plant in the foreground. It's already decaying. And this is a remarkable thing about these, is how well they are preserved. And you can use these to actually reconstruct how the glacier behaved 6,000 years ago. In 1984, there was no lake here, but the old plants we collected here dated about 4,700 years. By 2011, an island had appeared here, and there were plants on that island. those plants were 6,300 years in age. So if you go back 6,000 years, it took 1,600 years for the ice to move from here to capture the plants on the other side. This retreat has taken place in the last 25 years. So it gives you an idea of the rate of change. And of course, this is happening around the world. If you go to the Himalayas, again, very hard to find old pictures, but here's 1921, and you see these mountain peaks, and you see the same place in 2009. Kilimanjaro in Africa. Anyone here been to Kilimanjaro? This is a spectacular tropical mountain, highest mountain in Africa. These are the glaciers. This was the northern ice field. This was in 2003, Furtwanger, the southern ice field. We drilled these back in 2000, and we've been looking at the photographs. The very first photograph that we could find was taken in 1912. These are glaciers coming down from the mountain. This comes up to 2006. First map was made in 1912, and that's the outer layers that you see here for the glaciers. And we've been mapping it regularly ever since we drilled there in 2000. So since 2012, we had lost 88.3% of the ice on the mountain, the area of the ice. And from the time we drilled in 2000 to 2013, we had lost 40% of the ice that was there in 2000. And it's more telling to look at how these glaciers are changing vertically. When we drilled Furtwanger, we put a stake all the way to bedrock. And that stake has been measured since we drilled there in 2000. And this is the thinning from the top down. It averages about a half a meter a year. Until 2013, the stake came out. And the ice that was there in 2000, you can no longer recover that history. And so we've lost 2 of the 6 drill sites over that 13-year period. This is what Furtwanger looked like in 1999 when we first visited the mountain. This is what it looked like in 2015. And you can see how it's broken up and more of the dark surface gets exposed and it accelerates the loss of the ice. The last place I want to take you is to New Guinea, to Papua, Indonesia. Most people don't know there's a glacier out there, and there won't be for much longer. The oldest photos we could find there were made in 1936. So these are the ice fields. By 2001, you can see how they have broken up. And with satellite images, you can look at how much ice was there. These are Landsat 5 images. This was in 1989. So the blue areas are the glaciers. 20 years later, in 2009, you can see how much ice has disappeared. When we drilled there in 2010, this is what the glacier looked like, and this was really a salvage mission to get what might be recorded in the ice. We drilled 2 cores to bedrock here, and then 1 from this dome. And in 2010, the glacier was about 32 meters thick. But what's amazing is what's happened since 2010. And so I'm going to show you, and you can watch in the last 6 years what's happened to this glacier. So here we are in 2010, and you want to look at this area here and watch these holes develop. And it's going to go to 2012, 2014 to 2016. And so you can watch what's happening to this glacier as you go forward in time over this very short period of time. And you can see how narrow this band of ice is getting. And by September of 2016, you can see it's separated into 2 glaciers. And the latest photo we have was taken on November 23rd, 2016 by one of my former PhD students. And you can see what it looked like in 2010 and what it looked like 6 years later. We estimate this glacier will disappear in the next 3 to 5 years at the current rate of ice loss. I'm going to bring you up to this year over in western Tibet. This is the ice field that we drilled in 2015. But a remarkable thing happened in the mountains just to the south here at 170 kilometers. This is the Arku Glacier and a lake here. And on July 17th of 2016, this glacier collapsed. And the ice moved out across the plain. It killed 9 Tibetan shepherds that were camped out there. And this eyewitness reports say this ice moved out here in 4 to 5 minutes, 6 kilometers. And we don't know of any place where ice has behaved in this manner. This is what the flow looks like. It was 17 million cubic meters of ice. Here's a person for scale when it went out across the plain. But what makes it really unusual is that 2 months later, in September 21st, the glacier just to the south of here also collapsed. And it was 100 million cubic meters of ice. So the question is, what's causing this? These glaciers have been polar. They're frozen to the bed. And we think one of the possibilities that they're going from being polar glaciers to temperate glaciers as the temperatures warm. And we looked at the nearest weather station, which is 290 kilometers to the southwest. And you can see temperatures have risen 1.5 degrees C in the last 5 decades. And if you look at the isotopes from the Glacier ice cap just to the north, you can see this enrichment taking place. But the beauty of the ice is it can give you a perspective. So if you look at the most recent period from 1940 to 2015 and project that back, these are 50-year averages, you see we're not even close to any other 50-year period over the last 1,000 years. So there's certainly a lot of evidence that this area is warming. What we think may be driving the loss of these glaciers is that if you look at the Intergovernmental Panel on Climate Change projections for temperature rise, that 3 degrees C is at the surface. If you get up to where these glaciers are located, you can see the projected warming is about 6 degrees C. So we believe they may be responding to that. So globally, we're losing ice around the world. This shows the loss of ice on all the continents. This is the total glacier decline, which has been about 2,300 cubic miles of ice, which is equivalent to about 27 millimeters of sea level rise globally. So tremendous changes, and then these are monitored. These are from 1870 to 1924, sea level was rising about 0.8 millimeters per year. In the most recent period here, 3.1 millimeters per year. And when we were at AGU this year, it's up to 3.3 millimeters per year. So this continues to accelerate. It's interesting to look at what the impacts of 1 meter of sea level rise would be globally. And this is on the low end of projections now for 2100. So all the red areas here are places that would be under the ocean. If you get 1 meter of sea level rise, that would displace 145 million people on the planet, and the estimated cost would be $941 billion. So these are really significant changes. So you can argue that there's a perfect storm brewing, and the ingredients are this 1,000+ year residence time of CO2 in the atmosphere. The climate system has inertia. It'll be another 20 to 30 years before we see the full impacts of what has already happened. There's positive amplifying feedbacks in the system. When you melt the ice, you absorb more radiation and temperatures go higher. And there's a fossil fuel addiction globally on the Earth. And you can talk about a alternative future with more renewable energies, cleaner air and water, enhanced economic development, and better jobs. But I can tell you that what people respond to are here and now. And if you just look in the US in the year 2016, the events that have occurred. This is a flood in Missouri on January 6th. And then through this part of the world, on January 23rd, you had this record snowfall that occurred. And the cost of these events are given in many of these figures. Then floods in Texas in June of 2016, impacting that state. And then in August of 2016 in Louisiana. And this brings about one of these human characteristics, that the consequences for individuals outweigh consequences for others. So if it's your house that gets flooded, then you pay attention to these changes. Then there was Hurricane Matthew come up the East Coast and the cost associated with that. And of course, the insurance business pays attention to these, the Munich Re, Swiss Re, and there's a history going back to 1980 up to 2015 of storms, floods, mudslides, extreme temperatures, droughts, and fires. And if you look at the cost, over the last 10 years, the weather-related losses have averaged $155 billion a year, of which $40 billion was covered by insurance. That means that taxpayers and residents pick up that difference. And so these are huge costs, but they bring another human characteristic, and that is immediate consequences outweigh delayed consequences. And I think when the cost of climate change becomes so apparent to so many people, then we start to pay attention to that. And so these are things that I think are changing our perspective on this subject. And then, of course, if you look at tropical diseases, they're spreading to higher elevations and higher latitudes. And you can look at the Zika virus here. When this diagram was made, it wasn't yet in Florida, and now it's in Texas. And as the temperatures warm, these organisms respond to those temperature changes. So I want to close on a positive note. There's a lot of things happening, very important changes in conservation, increased efficiencies, four-cylinder and hybrid cars, electric cars, Tesla, Google, Apple, they're all working on this technology. Renewable energies, everything from fuel cells to even zero-emission coal-burning power plants, solar, geothermal, ethanol, and wind power. Mass transit, light rail systems, housing designs toward more compact cities so you don't have to use as much energy, nanotechnology, LED technology. And the important thing is that when these things get implemented, and I'm from Ohio State University, it's one of the largest public universities in the US, and at Ohio State we have over 70 student organizations looking at sustainability. And so we now have 19 gold, silver, and LED certified buildings. Wind energy now meets 21% of the main campus energy needs. We have geothermal wells that power some of the resident halls on campus. We have zero waste management for a big football stadium. The Zanger bike sharing program, electric vehicle charging stations, and Mirror Lake, which is not unlike the lake you have here, has now just switched from potable water to well water. So there are a lot of things that can be done and are being done at the local level. So if I'm asked what are the greatest challenges we face in the 21st century, I think it's learning how to get along with each other on this planet. That's something that's been with us for a very long time and something that we seem to be going in the wrong direction in right now. But also learning how to get along with our planet and to preserve the lifestyle that we know and love, and it's a great planet to live on. And the important thing about these are these two challenges deal with human behavior, and therefore they're very closely related. And so interdisciplinary research, understanding what drives us, becomes a very important part of this. So finally, if we've learned anything from our international space programs, it's how unique this planet is to life forms as we know them. But we also know when it comes to global climate change, nature is the timekeeper here. And we don't really have a clock, but we have a lot of evidence that that time is passing and the system is changing. So we don't know how long we have to deal with these issues. But I think at the end of the day, we will deal with them because we have no other choice. So thank you very much for your attention.
We should all thank you for your service, and I know you've contributed to some Vatican reports. And I have a friend in Piscataway who is the head of a group for 804 people that have had heart replacements. He couldn't come tonight. He would love to have seen you and talk to you about your experience. Can you relate some of that to the people?
Yeah, I think I had a heart transplant 4.5 years ago. And it taught me a lot about human behavior, because when I was told that I had congestive heart failure and that I was on a threshold and I was going to drop to another threshold if I was lucky, but in my future I had one choice and one choice only, and that was to get a heart transplant. And another doctor had told me 20 years earlier that I had exercise-induced asthma, and he had told me that the beauty of this is there was medicines for this, and there was nothing in the world you couldn't do if you had the right medicine. So I chose to believe the asthma doctor because, and I fought this cardiologist for 2 years, running expeditions to New Guinea and over in the Alps. But one day in the Alps, I just couldn't walk from the tent to the drill site. And I got back and ended up in the Ross Heart Hospital, and initially got a turbine put in my old heart. And so I ran on a computer and an electric system for 6 months, and gives you a whole different view of a persistent power supply, because if it stops, it stops. And but that bought the time to get a transplant, to find a good match. And then I went in 2012, was in the hospital 2 weeks to get a transplant. And then this drilling over in China in the Western Kowloons at 22,000 feet, that's a world record for a heart transplant patient. But part of this, we now have in this country 2,500 heart transplants every year, and most of these people retire or they can't get a job because of this condition. And so one of the messages are to my fellow heart transplant patients and the rest of the world is that, yeah, you had a problem, but you took care of it. And when it's taken care of, you can live a normal life. And so, yeah, I think, but what it also showed me when it comes to climate change, it didn't really matter what I believed or what anybody believes. It is only what is that we deal with. And climate change is a matter of chemistry and physics, and it's what is that will determine the future. So yeah, it was, I wouldn't want to do it again, but I learned so much from that experience, yeah. Okay.
So when you look at the physics of glacial decline, is it that it's snowing less, or it's just melting faster, or is it both? This argument had come up initially when we worked on Kilimanjaro, because there are people who would argue that it's precipitation driving the loss of the ice and not the rising temperature. But the fact is, precipitation and temperature are linked. This is climate change, and in the tropics, generally speaking, when it's warm, it's dry, and when it's cool, it's wet. So these things are linked. And my argument has always been it doesn't matter whether you're in a wet place or a dry place in the tropics. All the glaciers are behaving the same. And it's always the bulk of the evidence that drives what's driving these glaciers. Short term, I think precipitation can cause them to increase precipitation, can cause them to advance, but long term, temperature drives the glacier. Yeah.
It was a very interesting talk. I really enjoyed it. I was wondering, what could you tell the students here to do if they're really concerned about global warming?
Well, I think this is something that all of us, we can make a difference where we live, in our choices that we make. Most importantly, it's important to vote and to get the right people into office. It's the beauty of a democracy. And there will be another election and things will change in the country. So, but also when we choose how we choose to spend our dollars, is extremely important in what we support in the community. But we can all work on with groups that bring about change. And the change is happening, and it will continue to happen because it's coming from the bottom up. I was out in Iowa. Iowa now gets 30% of their electricity comes from wind. You go to Texas, they have more wind farms in Texas than any other state in the union. So these changes are coming, and this is the pushback is nothing new. All you have to do is go look at history. You go back and look at, we used to heat our houses with fireplaces. There was an industry of stone cutters who cut the stones for those fireplaces. There was another industry that produced wood for those fireplaces. And when Benjamin Franklin came along with a more efficient wood-burning stove, there was all these negative things about this heat was bad for your health, but it didn't change. And so I think that there's always this pushback with anyone who has an industry and they're making money from it. They don't want to see things change, but things change anyway. So it's just a matter of time.
Hi, that was fantastic. Thank you. My daughter's a geographer, so I came for her benefit. But
okay.
Anyway,
Well,
can you tell me what? So I also had a grandfather who was a coal miner. Can you tell me what is a carbon-free coal plant?
This is where you capture the carbon that is produced when you combust it, and the technology is out there, and I think this is the beauty of when there's a need, human beings are very innovative, and there's ways to do things in a different way and capture that carbon. And I have to tell you, I grew up in West Virginia, and I came to Ohio State to study coal geology because I was looking for a job. But I also know that in West Virginia, where I go back to talk to young people, that the maximum number of coal miners worked in those mines in 1924. The numbers have been increasing ever since then. They were replaced by technology. Maximum coal production was in 2002. And if you're looking at the future, you got to look at engineering. You got to look at the new technologies. And even in our state, which is Republican, we have a Republican governor. He just vetoed a moratorium that the Republican Congress put on renewable energies that transfer a certain percentage every year in the power supplies have to come from renewable energies. And the governor stopped them. And so we continue in this process. And the reason he did it was that is creating jobs. The coal mines are not creating jobs. I mean, it's an economically driven decision in many ways. Yeah. But there are ways to capture this CO2, and same in the oil business. I mean, a lot of these companies like Shell captures the CO2 that's coming out of oil and then pumps it back into the ground. And so there are ways that we can clean up the use of fossil fuels. And there are certain things that those fuels are very viable and very valuable for. So I think we have, I like to think that there's no silver bullet to this issue, but there's a lot of silver buckshot out there, and which one you choose depends on where you live. Yeah.
Well, okay, let's thank Lonnie again.
Yeah, thank you.